I'm Ava.
And I'm Beth.
This is Calculus AB.
Are you ready to graph this function? I am. Approximating an area under a curve using rectangles when we're given the equation y equals x squared on the closed interval 2, 6. And we have to estimate using only 4 left rectangles. So to start, we made a table of values by plugging in numbers on the interval. So we did 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. Then, once we had all the y values, we went to the graph and we graphed the rectangles. Wait, what? Graphing the rectangles? That's complicated. How did you start? So the start, we just labeled the x-axis and we drew the curve. We went to the left side and we went up to where the value hits the curve and went over.
So the way you do left rectangles is you start on the left side. The leftmost x value is 2. So you start at where 2 meets the graph and then you draw a line over to the right. And then you go back down at 3. And then you do the same thing. You go up in 3 at 3 and then go over to the right. So it's up and over to the right when you're doing left rectangles.
It's important to note that the left corner of the rectangle is touching the graph for left rectangles. The bases are only 1. How did we find the bases? We did b minus a over n, so 6 minus 2 over 4, which equals 4 over 4.
A is the starting number in the interval, and b is the last number in the interval. So 6 minus 2, and n is the number of rectangles. And as it says above, it's 4 rectangles. And 6 minus 2 divided by 4 is 1.
How do we actually evaluate the area?
The area of a rectangle is base times height. We're going to sum up these areas all together to get an approximate area under the whole curve. The heights are just the y values, and so we have 4, 9, 16, and 24. Obviously, 36 is not included because we started from the left side. If we had started from the right side, it would be different. So anyway, we add all of these up, and we get 54 units squared as our final answer. And then one more question now, is this an overestimate or an underestimate of the actual area? And what I did is I shaded in the space that's left underneath the graph, and we can see that there's extra space that hasn't been accounted for under the curve, which means it's definitely going to be an underestimate. Now try estimating the area using 4 right rectangles. So right rectangles are going to be the opposite of left rectangles. As you can see, this is going to be an overestimate because the rectangles go above the function. The bases are still equal to 1, so it's just 1 times the height of each one. 1 times 9 plus 1 times 16 plus 1 times 25 plus 1 times 36 equals 86 units squared. And one thing to remember, with right rectangles, you're always going to have the furthest right y value included in your equation. So the 36 is going to be in there. And that 4 value, the height of 4, isn't going to be in there. That's only in there in a left rectangle. So that's something to keep in mind. Now for midpoint rectangles, it's a little less intuitive. So you look in between each x interval. So you're going to go to the point 2.5 and go straight up into your curve, make a point there. That's going to be the height of your rectangle, where 2.5 hits the curve. So then you can draw a line that is level with that point you made, and that'll be the height of your rectangle. So that's how you make your rectangles. And with midpoint rectangles, you don't have to worry about leaving out the left or the right side. There's exactly 4 midpoints between the 5 x values given. So to solve this, you do it the same way you would. Bases still equal 1, that hasn't changed, but our heights are different. So to find the heights, we plug these new midpoint x values into the function. The original function is x squared, so you can do it in your calculator. So you have to find what 2.5 is squared, and then you do the same 3.5 squared, 4.5 squared, 5.5 squared. All of those are times 1, and then you add them together and you'll get 69 units squared as your area under the curve. And then once again, the midpoint estimate is more accurate than left and right rectangles are, but it's still going to be a little bit of an underestimate. You can kind of see by what I filled in on the graph. But if you were to actually test it and compare it to the actual area, you would find it to be an underestimate.
When f of x is increasing, when is it an under or overestimate? For left rectangles, it's an underestimate, and you can test this out by drawing the rectangles yourself. And for a right rectangle, it's an overestimate. The same strategy applies, testing it out by drawing them yourself. When f of x is decreasing, left rectangles are overestimate, and right rectangles are underestimate.
Increasing and decreasing are opposites. So you know that when left is an underestimate for increasing, the opposite will be true for decreasing. And same applies for right rectangle. Alright, approximating area under a curve with trapezoids. Whoa, we're changing things up here. Yes, trapezoids are a thing. So, the first thing to keep in mind is the area of a trapezoid is different. And the areas are what we will be eventually summing together to get this. So we need to know the area of a trapezoid. And it's 1/2 times the height times base 1 plus base 2. So I didn't give you an actual function. This is just a rough graph. And the graph looks like this. You can see there's a point at 0, 1, 2, 6, it looks like, and 4, 8. So approximate the integral between 0 and 6 of f of x dx using 3 trapezoids. All this problem is asking is between 0 and 6, that's the interval, find the area using 3 trapezoids on that interval. So first thing I did was draw in the trapezoids. And first you need to know what the width of each one is. It's going to be 2. How did I know that? I found the change in x. So it's going to be, remember, b minus a over number of trapezoids. Okay, so 6 minus 0 divided by 3 is 2. So each trapezoid is going to have that width, or kind of a height in this case, of 2. So that equally divides up this graph into 3 parts. And so I kind of just did a rough drawing of each of the bases of the trapezoids. And it's important to note that with trapezoids, they share bases. Next thing I did was measure what the lengths of the bases are. So the first one goes up about 6, then the next one goes up to 8. And I decided to make that last point be at -1/2. My drawing isn't very clear, but basically to make it a little trickier on you guys, that part that's under the x-axis is going to sort of be a negative base. Just like with summing rectangles, we find the area of each trapezoid and we add them together. So the first one, it has a base of 1 on one side and a base of 6 on the other side. So 1 plus 6, we add the bases. All the heights are going to be 2. In this case, the change in x is the height. So we can multiply the whole sum by 2 and by 1/2 because it's 1/2 of the height in the trapezoid equation. So we have 1 plus 6, and then we add that to 6 plus 8 because those are the bases of the second trapezoid. And lastly, this one on the right here is kind of tricky, but it's actually 8 is the positive part, and then we have to subtract that 1/2 to just get the area that's above the x-axis. And then I just simplified that equation, and it will simplify to 28.5 as your final area. Once again, this is only an approximation.
Sigma is a Greek letter and it means sum. In the example below, we see that the starting point is I equals 1, so 1. Whatever is in the bottom of the sigma is going to be the starting point. The last number in the sequence is always going to be on the top, and in this case, it's 6. The equation is in the middle, which is I squared. To evaluate the sum, you square all numbers. You plug in 1, 2, 3, 4, 5, and 6, and you square them because that's what the equation is, and you get the final answer of 91. Okay, evaluate these sums. So the first one, we have I equals 1 as the starting value. So the start, and it ends at 4. So what does this equal? So we plug in 1, 2, 3, and 4 to get the answer, and then we square all of them because that's what the equation is, and we get the final answer of 31. The second example, we have the same starting and ending point, but the equation is different. It's a variable b. So what you do is you add b plus 2b plus 3b plus 4b. Why do you add this up? And why aren't these just integers? It's because b is some variable. We don't know what b is, so that's why you just do that. This gives you the final answer of 10b.
Okay, let's talk Riemann sum formulas for area under the curve. Basically, this is a synthesis of the information you've already learned, sigmas, and finding areas with rectangles, and we're combining the two together. What if we could make it way easier? Instead of finding the individual area of every rectangle, come up with a formula that does the same exact thing. And we're using sigmas for this because sigma is all about summing things together. So first of all, we're going to look at the formula for the left rectangle. There's only a few differences between left, right, and midpoint rectangles, but I'll be sure to cover them. So for left rectangle, we have our sigma, because that indicates that a sum is going on. And then on the bottom, we have the k equals 0. That's just our starting point at 0. Remember, with left rectangles, we start at the leftmost value, x value. We start in the left-hand corner, so of course we're going to want to start at sort of the 0 starting point. And then we have our n minus 1, because remember, since we're starting at the left, we're not going to make it to the rightmost x value, so that's why we need to have that minus 1 in there. And then, of course, whatever our f of x equation, within the x we're going to have to put in whatever the first left is, your a value, and then you add it to the change in x times k, which is what you'll be plugging your n values into, and then times change in x on the outside. Now, there's two different ways you can go about the formula for the right rectangle. You can do it in the same way as for the left rectangle sum, in which you have your n minus 1, your k equals 0, but instead of having your a, you have your first right value, which means, because remember, you skip the sort of the leftmost x value with right rectangles, so you put your first right in there instead, and then times change in x. Or there's another way, which is the way I like to do it. It just makes more sense to me. It doesn't work for everyone. You can have that sigma, and instead of an n minus 1, you have an n, because with right rectangles, you go all the way to the right, so you don't have to subtract the last number in the sequence, and k equals 1 in this case. And with k equals 1, that kind of means you're skipping that leftmost corner, because remember, it's a right rectangle, and then f of your first left. So then with this equation, you get to keep that a plus change in x times k in the inside, and that's why I like it, because that doesn't change. The only thing that changes is instead of n minus 1, it's n, and instead of k equals 0, it's k equals 1. Either one will work fine for right rectangle. It's completely a personal preference. Lastly, midpoint rectangle is a little different. So you keep the same setup as left rectangle. You have your sigma, you have your n minus 1, you have your k equals 0. But then, instead of your first left, you have your first middle, plus change in x times k, all times change in x. To find the first middle, you take your a value that you're given, and then you add it to your change of x divided by 2, because remember, it's a midpoint. Your a value is your leftmost x value. Your change of x is the width of your rectangle, but you need to divide that by 2 because you're only going halfway into your first rectangle, and that's what your first middle is. And lastly, I just drew in again that b minus a over n being the number of rectangles, that is going to be equal to your change in x, and that's important to know as well. Just to clarify, the change in x is the width of your rectangle. Approximate the area under the curve. F of x equals x cubed, and the interval goes from 2 to 5. Use 9 rectangles and a midpoint sum to solve this problem. For approximating area, we need to know the b, the a, and the n. So we already have b and a. It's 5 is b, and 2 is a, and n is the number of rectangles, and they give that to us in the problem. So n is 9. And then to solve for the change in x, we do that little equation b minus a over n. So it's going to be 5 minus 2 over 9, which will simplify to 1/3. Now, since this is a midpoint sum, we need to use the midpoint Riemann sum formula that I showed you earlier. So that's going to be your sigma k equals 0 with an n minus 1 on top times f of the first middle plus change in x times k, and then the whole thing times the change in x again. So we have the change in x. We already got that. The change in x is 1/3. And I drew that little sigma with the 8 on top because 9 minus 1 is 8. And then I like to put the change in x on the outside of the sigma, so I have the 1/3 on the outside. Now, how to find the first midpoint in a midpoint sum? So, to find the first midpoint, you add a. A is the starting point, of course, plus half of the change in x. Because we're only going halfway. We're not going the full rectangle, we're going to half of the rectangle. So a plus half of change in x is going to give us our first midpoint value. So a is 2, and we add it to 1/3 divided by 2. 1/3 divided by 2 is 1/6. So 2 plus 1/6 equals 13/6. Now I have the first midpoint value, and I add that to change of x times k. 1/3 times k, and then I cube the whole thing because that's what the function calls for. And then I plug that into my calculator. No one would expect you to solve this problem by hand, and you get 151.958 units squared. And you're done. Hope that midpoint summing was fun.